Hopefully these two didn't take us very long, or once we started thinking about them, we knew what the answers were, because they should be quick answers for the test that we have on Wednesday. If you didn't remember that I told you about the test, this is a quick reminder. When we have a table, or just in general, how are we supposed to tell the difference between our types of functions? Rate of change, right? And so, if it is linear, what kind of rate of change does it have? Constant additive, right? We've got to remember that. If it is linear, it has a constant additive rate of change. If it is exponential, Jeremiah, what kind of rate of change are we looking at? If it's exponential, what kind of rate of change are we looking at? There we go, right? So we need to be looking for that multiplicative rate of change. And if it is quadratic, then what are we looking at? Okay, so we got to know this. KJ, what kind of rate of change are we looking at if it's quadratic?
Constant additive.
Okay, what do y'all think? Constant additive? Nathan, you immediately shook your head no. Why? You went to shake your head no. Why? Oh, I saw it. Maybe it was unintentional. Oh, okay. Anybody?
I don't know. Well, because it wasn't constantly adding.
Well, but the question is does a quadratic function have a constant additive rate of change?
No, well, on the second differences it does.
And so that's where we have to be careful on the second differences, but the second differences isn't where it's isn't the rate of change. Where do we see the rate of change? On the first set of differences, right? And so if the second set of differences is constant additive, what do we know about the first set of differences?
It's going to add.
The second set of differences was constant additive. What kind of function had a constant additive rate of change? So if the second differences are constant additive, the first set of differences are linear additive, right? Those are the things we want to pay attention to. We need to be careful. So I see a lot of us recognizing it as quadratic, and I do see this idea of it's going up and then down, or down and up. We need to be careful about that, because that would earn us a different number of points based on the accuracy there. But if we are talking about a quadratic function, we need to recognize that as a linear rate of change, not a constant additive. We'll talk about that in a second. We are saying that the second set of differences is constant additive. And so we do see the idea of it creating a parabola. So let's look at the table again all together. Alright. So looking at this table, and KJ, originally you were thinking exponential because you didn't think it was linear or quadratic, right? But is there anything we could multiply 8 by to get 6? Same thing, 6 to get 5? Can't multiply anything there, right? If you look at it, remember, what's that multiplicative rate of change called? A common ratio. So if I do a ratio between 6 and 8, I get 3/4. If I do a ratio between 5 and 6, is that the same ratio? That's what we want to quickly check. Is it a common ratio? If not, yeah, it's not exponential. Okay, but what could I do to go from 8 to 6 then? Subtract 2, 6 to 5. And notice for those of us who said it goes up and then down, it's going down, decreasing, then it's going up. Is that a constant additive rate of change? No. But to go from -2 to -1, I am adding 1, and then adding 1, and then adding 1. Remember, this set of second differences is constant additive. But notice I don't call that the rate of change. The second differences is constant additive. The first differences, that's my rate of change then, is linear. Right? We need to remember, constant additive is linear. So constant additive here, linear additive rate of change here, and so the function is quadratic. Does that, a quick little recap, help us prepare for our test a little bit better on Wednesday? Details we may have forgotten or missed? Yes, Mr. Kenny. Great. All right. Question 2. let's look at this, our answers here. So exponential, we got one person who just said exponential. Exponential because it has an exponent, which is repeated multiplication. It has a curve and the rate of change. It is an exponential curve, and 3/2 is being squared. Is there any language up here that we want to push on and be careful about? Not necessarily that it's completely wrong, but we need to be careful with this language.
Has a curve.
Okay, why do you say it has a curve? Why do we want to be careful about that?
I don't think it's the only one that has a curve, right?
Does any other function have a curve to it? Well, this is exponential. Quadratic, right? The quadratic has a parabola, but an exponential has a different kind of curve, right? And it says it is a slight curve, but literally we would call this kind of curve a what? Exponential curve. That's it, right? That is the name of the curve. And I Googled it because I was really curious. I was like, there's got to be something other than exponential curve. Nope, that's it. It's called an exponential curve. Because of the exponent, that's some good logic. There was one answer that was so close that I did want to be 100% right, but is not quite right because they not only identified the fact that there was an exponent, but they told me what the rate of change was, or what they thought it was. You want to see which one? The last. The one that has numbers in it. But notice the 3/2, is it being squared? No. Right? So go back and look at that graph. Well, it's being repeatedly multiplied, which is that multiplicative rate of change. But notice, right? Is it being squared? No. Remember, an exponential always has what as the exponent?
Okay.
A variable in general, right? There needs to be a variable in that exponent in order for it to be an exponential function, because the whole thing there is that we are repeatedly multiplying an unknown number of times, right? Did this graph freak anybody out? Because they're like, there's something wrong about that exponential? No? Okay.
I mean, yeah, I know those upside down.
Okay, that's what I did want us to notice. It is upside down from what we're used to seeing, but is it still exponential?
Yeah.
Yeah, because remember, it's that multiplicative rate of change that defines whether it's exponential or not. All it was is I made it a -2 for that y-intercept. And so because it started at -2, every time I multiply, it's going to get more negative. But it's still exponential. It's just known as a reflection. Any questions before we move on? Do we understand the different equations a little bit, or functions better? Okay, so remember, we need to know these things before your test. And you have 2 understanding checks already for the unit. The first one was on writing the equations of linear functions and exponential functions and identifying linear, exponential, and quadratic functions. You have that with feedback. I would study those things. You also have an understanding check on the different forms of a quadratic function or equation. I would study that, and then you'll have one more understanding check today that I will grade and give feedback to you so that you have it for your test on Friday, or test on Wednesday. And once again, it doesn't matter what you made on the understanding check, as long as you learn from your mistakes, you improve and get better. Okay, you gotta investigate your mistakes and make sure you understand how to improve. Going back to the slides. That's third block. Okay, quick note about homework. Y'all do have homework that is due this week. It will be the only homework that you have this week, so let's make sure we get it done. But it will not be due until Wednesday. The reason behind that is, if I made it due tomorrow, there's no point in me collecting it tomorrow because I can't give you feedback before the test. However, I want to make sure you do the homework so that you get the practice in before the test. Does that make sense? We good with all that? Any questions? Yes, ma'am. Okay. And so we'll wrap up lesson 6, I want to believe, and have an understanding check. I also have some practice that I'm going to go ahead and give you that we'll work on in class all day tomorrow. So remember, the whole thing is, we learned about this new number on Friday, I believe. Maybe it started on Thursday. What new number did we learn about?
Imaginary.
The imaginary number, I. What do we mean by I? So I is -1 squared. square root of -1, right? We could already square a -1, we get 1. But we have not been able to deal with the square root of a negative before. That's that imaginary number is what creates a complex number system. Now, when we say imaginary, does that mean it doesn't actually exist? Nope. It's a very real number, it's just the name of the number system because we didn't think it could exist originally. So we need to be able to determine which sets numbers belong to, properties of the set of complex numbers, and do some practice calculating complex roots. So I want to point this out. When we are solving quadratic equations, nothing has changed from what we did previously, except for one thing. Does anyone remember, let me just quickly show this. Which of these graphs would have complex roots? A, B, or C?
A, C, B, wait.
What is complex roots?
And don't you gotta press the x-axis?
Say it again.
Don't you gotta press the x-axis?
Typically, we would be on the x-axis, but I want you to think about this. If it is hitting the x-axis, does that mean it's imaginary or does that mean it's real?
Real.
Remember, every number on the coordinate system, remember y'all freaked out about the word Cartesian coordinate system, I believe, on Friday. Every number on the Cartesian coordinate system is a real number. So these roots have to be what?
Real.
Real. This root has to be
Real.
real. So if we're not touching the x-axis, aren't there still, how many roots are there always going to be? 2. But are there any real roots here? So there would be complex roots here. Does that make sense? How many roots are there always? There's 2. We see the 2 right here. Real numbers. We see 1 here, but remember we talked about that, it would just be like x minus 3 squared, so it would have 2 at that number 3. But do I see any x-intercepts here?
No.
So the roots are not x-intercepts, because they're not real numbers, they are complex numbers.
So, B,
Yes, is where we have our complex roots.
so they, okay, so those two are, don't put these real numbers.
If you ever have an x-intercept, those are our real roots.
Okay.
If you don't have an x-intercept, and that's something we wrote in our notes on Friday, if you don't have an x-intercept, that's when it would have to be imaginary roots. Does that make sense now? Okay. So I will point this out. What are the 3 methods we have already studied to solve a quadratic equation? We wrote, so remember we rewrote the standard form into vertex form, right? Because we could then solve something like x minus 2 squared plus 8 is equal to 0. Once we get into vertex form, we could easily solve it. We could do factored form. We could not solve it. Remember, we always graphed it when it was in standard form to get the vertex form or to get the factored form. The quadratic formula, right? And so then you need to know that quadratic formula, we'll practice with it later. But are there any of these methods that will not work then for complex roots?
Minus B, because on the paper it just said B.
Nope, minus b. It says minus b on there. Look again. Yeah, negative b plus or minus square root of b squared minus 4ac all divided by 2a. Are there any of these methods that will not work to find the complex roots? What do you have to have in order to use factored form, or to get factored form? You have to have x-intercepts, right?
Yeah.
Well, if it's complex, do we have x-intercepts? So can we use factored form?
I thought you said it was 3.
Yeah, you can write it in vertex form to solve it. You can write it in factored form to solve the equation, or you can do the quadratic formula. But if we have complex roots, can we put it in factored form? No. Right, so remember there are 3 different methods. However, factored form doesn't help us when it's a complex root. Okay? So quick little recap there. This is where we wrapped up on Friday looking at these number systems. And so don't forget both real numbers and imaginary numbers fall under the complex number system. But what we're about to do is actually look at practicing putting some numbers in, or identifying what numbers go into what sets. So, I don't remember which page this is. What, you already have it open? M1-97, right? M1-97 is where we should be looking in our textbook. Okay. Let's take some quick notes here. Have a whole class discussion around these ideas. So if a number is an imaginary number, right, then is it sometimes, always, or never a complex number?
Oh, that's the next
My bad. So M1-98 then?
I just re-going over things because we took notes on this.
Didn't we finish taking notes on this?
one. We didn't do that part right there, we
This.
took notes on that other part right there.
We took notes on all these number sets, right? So we're doing M1-98 now, looking at answering these questions.
So what
KJ,
was the top one?
say again.
What was the top one?
Well, the complex numbers, what did we write? I mean,
Oh, we didn't write anything on that one.
on the complex, remember, a complex number is any real number or any imaginary number, right? So a real number is going to be something where it's like 3 plus 0i. We can't have the imaginary component, right? So that it understood to be a 0. To be an imaginary number, it has to have the imaginary component. A complex number is any of those. A complex number is either a real number or an imaginary number. That's it. Okay? So, complex numbers is the biggest overarching number set that we have. So if a number is an imaginary number, then it is always, sometimes, or never a complex number. Which one?
Say it again.
Always.
So if a number is an imaginary number, then it is always, sometimes, or never a complex number. Here's imaginary, that's an example. Is that a complex number?
Yes,
Will it always be a complex number?
yes.
Yes. You cannot make an imaginary number that's not complex. It is always complex. Remember, complex numbers are that overarching group of real and imaginary. So if it's imaginary, it is complex. However, here's the flip side of it. If a number is a complex number, then it is always, sometimes, or never an imaginary number.
Never.
Can anyone create a complex number that is not imaginary? Yeah, this is complex, isn't it? Is it imaginary? No. So remember, complex is the combination of both the real and the imaginary. So there's a real number, it's complex, but it's definitely not imaginary. So it is sometimes. So there are complex numbers that are not imaginary. And you might want to show that example next to it, right? Something like 3 plus 0i, complex but not imaginary. It's all about explaining so that you can understand it later. Alright? So if a number is a real number, then it is always, sometimes, or never a complex number.
Always.
Always. Alright? That real number is always going to be complex. If a number is a real number, then it is always, sometimes, or never an imaginary number.
Never.
Never, right? That's the whole thing. They are completely different sets. Just like, can a number ever be both rational and irrational? No, they're completely different sets. They're next to each other, and they're different sets of numbers. If a number is a complex number, then it is always, sometimes, or never a real number.
Sometimes.
Sometimes, right? Again, here, that's a complex number, but that's imaginary, it's not real. So it's sometimes. So some complex numbers are real numbers. LaShannon, if you want to go ahead and move, you could.
Mr. King.
Yes, ma'am.
I would say he'll be like, because he's coming back from his leave from down there.
Gotcha, but he'll be here today?
Yeah.
Okay. Who else is missing from your group?
Cameron.
And Cameron. Has anyone heard from Cameron? I'll just leave it where they are now, or 4 now. So here's the thing, we do want to take a few minutes to practice identifying some number sets. You will have to do this on your test. These should be the easy problems, okay? The number 3, what is the most specific number set that it belongs to?
Really?
Okay, it definitely belongs to the reals. Is there anything down here that it also belongs to? Notice it's whole,
Neutral?
it's natural. Natural counting systems. So what I always do is I start with the most specific number set it is. Notice I'm using the symbols. If you don't remember the symbols, you can just write the name out. I'm totally good with either one. So you can put the N, or you can put natural number sets. What else does it belong to? Whole. Right? If it's a natural number, it is also a whole number. It belongs to the integers. Belongs to the rational. And so I want to point this out. If you can remember this diagram, it makes it really easy, because if I start here, I can just follow it all the way up, right? Rationals, anything else? Real numbers. Keep following it up. Anything else? Complex numbers. There it is. Okay? Now in contrast to that, C, what number set does that belong to?
Imaginary?
Imaginary or irrational? How do we know it's imaginary? The whole thing is as an I, right? I said C. Were you looking at C? Okay, sorry. I skipped B on purpose. I want you to do that one on your own. But yeah, notice C, it has the I, so it has an imaginary number. Does it fall under any other categories? And so it's automatically complex, right? So work within your groups, try to finish up the other 4. Hopefully it only takes a few minutes. And we'll come back together in a couple minutes to go over these and make sure that we all have them correct. So identify those number sets. Make sure if you use the symbols, you know what the symbols stand for. If you use the words, that is perfectly acceptable too.
This is imaginary.
You good with F being imaginary?
Complex.
Okay.
Yeah.
Don't forget, we want to be collaborating, talking, discussing. It'll help us make sure we understand it better. You're doing well. Talk with your group. Is that an A? What's that symbol? So why is it R minus Q? How do you know?
Rational, real, and complex.
How do you know it's irrational? So you're only good.
Since it's rational, it'll be real and complex. Because it is the sum.
So so remember, if it's a square root, you can take the square root on your calculator, right? To check that, so square root of 7. Put that decimal in there and get a decimal. But notice, like, there's some decimals there. If you go up and you grab it,
Come on.
it has even more decimals. Is it repeating?
You said B?
It's probably not terminating. But the other thing to remember is
Well, it's,
the square roots in general are irrational. When's the only time a square root is not irrational?
yeah, it's irrational. So,
Right, so the square root of 16, that's the same as 4. Okay, every other time a square root's gonna be irrational, or a root in general is gonna be irrational. That's an important thing to notice.
seven. Not a whole number. That is. Maybe. irrational, because it's a ratio. But if it's, well, kind of, irrational says it's a ratio of two integers. So, would it be integers of?
Alright, so I've already given the answers for B through F, and are there any questions about those?
Oh, E,
Yeah,
yeah, E, we were confused if it would be integers, because the notes we wrote down on rational, we like circled ratio instead of ratio of two integers.
right. So if you, that's a good question. So 7 divided by 8, notice that's an integer, right? That's an integer, but when I do the combination, it's the ratio of two integers, but it's not one integer. Does that make sense? The whole point of rational is that it is a ratio of two integers, but it's not an integer itself. So that's a really good question. Okay, so moving from there, I decided to make one more that I want us to think about. Jeremiah, gut instinct, right? You don't have to have this right, just gut instinct. What's odd number set you think this might belong to? What did I say? I said Jeremiah, didn't I, or did I say Delani?
No.
Okay, I'm like losing my mind, I'm so tired. Any number sets? None at all? There's two that we should know automatically. Any guesses which one of those two? I'm gonna come back to you for the other one. Give me one, KJ.
Irrational.
Why irrational?
It's square root.
Okay, so irrational, does anyone wanna push back on the irrationals, the real minus the rationals?
Yeah, no, it would be rational, because 64 squared is 8, it goes 8.
Be careful with the language. Square root of 64 is what?
It goes,
A,
it's 8, so it would be rational.
What do you think about that, KJ? Right? So can we just see a square root and automatically say, hey, that's irrational? No. It's only irrational if it's not a perfect square. That's the reason why I created this. Does that make sense? But before we even get to that, there is a real number set that, or a number set I should have said, that we should automatically know that this fits into. Huh? Imaginary?
I mean, I thought a real number, it had to be one number in real, without any symbols behind it.
Integer.
Okay, maybe that's not the number set I was thinking we should automatically know.
Rational.
Not the one I was thinking we should automatically know. Hey, does anyone see a number set that every single one of these falls into?
Complex.
Oh, every single number that we've studied is what?
Complex.
We should know it's complex, right? Does that make sense, Jeremiah? Like, that's what I was looking for us to recognize is that has to be complex because it's a number that we're dealing with. Okay? Now be careful. Real does not mean that it doesn't have anything else going on with it, because could I simplify this expression? Very much so, right? What makes something real if it doesn't have what? I. Does this have an I?
No.
So what should we automatically know it fits into?
Real.
The reals. We should automatically see, hey, it's a complex number, but hey, it's also real, because what does it not have? An I. We good with that now? Okay, so we got rational. Notice we do want to simplify, because what is negative 8 plus 8? 0. Notice we can simplify it to a single number.
Whole number.
So it's a whole number. What else?
Integer.
An integer. Is it a natural number?
No.
How do you know it would be a natural number, but you know it would be a real number?
Natural
Naturals don't have
numbers
zero.
don't start with 0.
Natural numbers start with what number?
One.
1. Whole numbers start with 0. We good with that idea? Any questions? Ready to move on? Okay, so you have to be able to identify your number sets. This is the last thing before we get into doing some practice of solving with quadratics, and before we wrap up with our understanding check today. So here in number 3, it says rewrite each expression using I. Well, what is I? Square root of -1. It defines the imaginary number set, right? And notice what they do in this problem that is actually given to us is you can use the number I to rewrite the square root of -25. So what is the first thing they do to that -25? You can see it in your book as well. Well, so notice there's already a -1, so what is it called when we take the things that can multiply to get a number and we separate it? Starts with an F. Factor it, right? So they didn't just magically multiply by -21 or -1. They said, hey, I have -25. That is equal to -1 times 25. Because again, what is the number I? The square root of -1. So we're taking that -25. We're rewriting as -1 times 25 because there is a cool little property about square roots, which ties into how they're connected to exponents, which we won't get into unfortunately. But I can separate that anytime I am multiplying within a square root, right, within what's called the radicand, that's what's underneath, I can separate it into the square root of -1 times the square root of 25. Right? So I am taking those factors and splitting it up into two separate square roots. Okay? That's something that I would make a note of here is anytime there is multiplication in the radicand, what we mean by that is what's underneath the radical, okay? Anytime there's multiplication in the radicand, inside radical, then the radical can be rewritten as, the product of radicals. That's all we're doing. Anytime there's multiplication in the radicand, then that one radical can be rewritten as the product of radicals. Okay? So with the square root of -4, are there any factors that I can take out of that -4, where I can rewrite it as factors? 4 times -1? Does that give me a -4? So I'm just rewriting that -4 as -1 times 4. Then, because I'm multiplying, I'm going to rewrite this as how many radicals? 2. It's already 1. I'm going to do the square root of -1 times. And from there, I'm just going to simplify. Jeremiah, how would we rewrite the square root of -1? Come on, this is fundamental. We got to know this. I'm coming back to you on the next one. You have to know this. Jaden? You don't know what the square root of -1 is. Really? LaShannon, can you help us out?
Is it -1?
It's I.
Oh.
The square root of -1. The whole point of what we're studying is it's the number what?
You made it sound like it was harder than it was.
No, I asked what is the square root of -1 and I got blank stares like we haven't talked about that. That's I. You gotta know that the whole point of this is the square root of -1 is I. It's an imaginary number. KJ, what's the square root of 4? Can I do that?
Yes.
What is it?
2.
So traditionally we write our real part first, so we would write it as 2I. Or the real factor. Factor. Okay? We're going to do B and C together. I'm going to have you do D on your own. Nathan, do you know of any factors that we could rewrite the square root of -12 as? Now, we're trying to take a square root. I do want to point this out. Lexi, are there any factors of 12 that we could take the square root of?
12.
You know what the square root of 12 is?
3.4641.
Is that exact or is that an approximation?
Approximation.
Right, that's an irrational number. Does anyone know a factor that we can take the square root of? Are 6 or 2 perfect squares that we can take a square root of? You can check it, but
4.
say again.
4.
Can we take the square root of 4? Yes. Notice, like, legitimately, we just need a perfect square, so 1 squared is 1, but that's not going to help me a lot. 2 squared is 4. Oh, so I can take the square root of 4, right? What is 3 squared? 9. 4 squared? 16. So we need to be thinking about those numbers so I can find something to take the square root of. Okay? So I'm going to rewrite this now as the square root of -1 times 4 times 3. I'm just going to rewrite it as a perfect square.
What did 3 come from?
Well, what 12 is 4 times what?
4 times 30.
Right. So I can't create a new number. I'm just rewriting that 12 so that I have a factor I can take the square root of.
Oh, so you just can't write a square root of 4?
You can't just like pull it out of thin air. I'm rewriting that 12 so I can take the square root. How many radicals am I now going to have?
3.
3. The square root of -1 times,
4.
not 4, square root of 4 times
Square root of 3.
square root of 3. Jeremiah, what's square root of -1? Seriously? I'm coming back to you in a second. Jaden, what's square root of -1? Thank you. Jeremiah, you're going to know that answer next time, right? Square root of -1 is always going to be what? I. Square root of 4? 2. And then, can I take the square root of 3? Is that a rational number?
No.
Nope, so I'm going to leave it as the square root of 3. Again, we usually put the real parts first, so 2 square root of 3i. That's it. You always put your real parts first, so I just rewrote as 2 square root of 3 and then the I.
That's the answer?
Yeah. Why are you confused by that?
Is this going to be on our test?
Yeah,
This is hard.
it is.
Seriously?
I don't even know what I'm doing. I'm just writing.
Yo,
I mean, it's not hard. It's just, I don't know what's going on. I know what's going on, but I'm a little slow, so you gotta.
not slow.
I am.
So let's think square root of -20. Okay? That 7 stays the same. How am I going to rewrite? Remember, what I'm trying to do, the whole point is rewrite each expression using what number? I. So I'm not going to write as the square root of -20. I'm going to factor out that -20 into what factors?
4 times -4 times 5.
Oh.
So I wouldn't do negative 4 times 5, because I want the square root of negative
Like, negative
1. So it would be negative 1 times 4 times 5, right? KJ, why did you immediately jump to 4 and 5?
Because, I just thought it was easier.
Okay, but why did you do 4 and 5 instead of 2 and 10?
I didn't think.
Should we do 4 and 5, or should we do 2 and 10, or just none of the above?
Does it matter?
Yes.
We can pick, or we just.
Yeah, that's,
What's the symbol that's above that radicand? What kind of root? Nope, what kind of root? Remember, this is, what's inside is called a radicand. What kind of root is this?
Square.
Square root. If we're taking a square
Oh,
root,
yeah.
we can take the square root of a perfect square.
oh, one of them at least got it perfect, what you saying?
So, if we're going to factor it out, you gotta have a perfect square.
Oh, 2 and 10, oh, there's no perfect.
2 and 10 are not perfect squares. Is one of these perfect?
Yes.
Which one?
4.
That's all I'm looking for. A factor that is a perfect square. Now, how many radicals am I gonna have?
3.
3, square root of
Negative 1.
-1 times the square root of
Negative 4.
4, just 4.
just 4. Right, we already have the negative 1 right here. Times the square root of 5.
Don't want to be negative in order for the negative 20.
But that's the negative. That's the point of factoring out the negative 1. Because Jeremiah, what's the square root of negative 1? I. Right? Square root of 4? 2. Can I take the square root of 5?
No.
Nope. So it's going to stay like the square root of 5. So 7 plus 2 square root of 5, I. That's it.
So you don't, what's the 7 for then? You don't do it with the 7?
No, you just did.
No.
Remember, I just asked you to rewrite the expression using what number?
Alright.
I. This would just be the real component of that complex number. This would be the imaginary component of that complex number. That's it. Does that make sense? We good? Any questions?
The only hard part is factoring. I'm not good at multiplication or finding square things.
You have a calculator.
Yeah, but like, what do I do?
Okay, that's a good question. So let's say I have the number 72. You want perfect squares, right? 1 squared is 1. What's 2 squared? 4. So does 4 divide into this number evenly?
No.
Notice the question, does 4 divide into that number evenly? Check it.
Yes.
Yeah.
What number? So we get 4 times what? 18. Okay,
Oh.
so that's one way to start it. Now, I will ask and point out, like, obviously you can't take a square root of 5, there's nothing else there. Are there any other factors of 18 that we could factor out? 9? Right, so we already did 2 squared, that was 4. What's 3 squared? 9. Does 9 divide into this number? So then I could rewrite this as 4 times 9 times 2. Is that the same as 72? So it's just taking that time to think through what are the perfect squares, dividing them in and saying, hey, can I divide it in? Now it just happened that 4 and 9 both worked here. So I'll create another example in a second where it's not as easy as that because you do need that other practice. But notice, so if I was taking the square root of this, all I would do is the square root of 4 times the square root of 9 times the square root of 2. 2 times 3 times the square root of 2. So I will point out something interesting here. Well, yeah, there's no negative 1. That would just give me the I. I was just trying to give you the practice of factoring, right? What is 4 times 9? Close. 36. The reason I bring that up is you could have been more efficient from the beginning and done the square root of 36 times 2. That's also 72. If you notice that there was a factor of 36. Because what is the square root of 36? 6. So does it matter how you break it down? You just have to find the perfect squares. That's it. That's it. We good with that idea? Okay. So square root of negative 75. I'm just making this up.
Oh,
Oh, come on, there's one place we definitely can be able to start.
36. -1.
Thank you, square root of -1 times 75. But are there any perfect squares in that 75? None? What's 2 squared? Does 4 divide into 75 evenly? How do you know? It's odd. Get an even number divide into an odd. No. Okay, so what about 3 squared? That is 9. Can 9 divide into 75? If you're not sure, test it on the calculator, right?
No.
75 divided by 9, not pretty. What about 4 squared? That would be 16. No. 5 squared. Hey, does 25 divide into 75?
Yeah, so five not
It's not 5, it's
Negative 3.
25. Right? 25 times 3 is 75.
Where's the 3 from?
It's 25 times 3.
Remember, we had to get 75. 25 was the perfect square we found, right? But take your calculator. What's 75 divided by 25?
So every number has a perfect square.
Third.
That's a good question. Let's look at it in a second. This is how you would break it down if it has a perfect square, right? So that's where the 3 came from. So square root of -1, Jeremiah, what is that? I, thank you. Square root of 25? 5 times square root of 3. So 5 square root of 3, I. Notice not every number has a perfect square. I can't take the square root of 3, so I leave it as it is. Does that make sense? Another example that we could look at, so I'm trying to think, square root of 30. What are some factors of 30?
Five.
5 times what gives me 30?
6.
6. Can I break down either of those into other factors? Not even at 6?
No.
2 3.
2 times 3.
Oh, well, yeah.
Are any of those factors perfect squares? No. So can I take the square root of any of them? So I wouldn't even split it up.
How do you get an answer?
You're done. Well, like you can't simplify anymore. That's your answer.
You can have a question on the test, like
Can you take the square root of any of those? So then why would you take the square root? That's all you have to think through. Right? Notice I took the square root of what I could take the square root of. That's it. Don't take the square root of something you can't take the square root of. Now, if it was the square root of negative 30, then I would do the square root of that -1. But again, I can't take the square root of anything there, so I just do square root of -1 times the square root of 30. So square root of 30i. Right? So I would do the square root of -1. Does that make sense? We good there? Do you want some individual practice time with this? Yes? Okay. Together or in your small groups? Together? Okay. And then do D on your own?
Wait a minute, don't leave us with the, don't leave us with the two.
It doesn't change anything.
It do.
It doesn't.
It
It
changed
doesn't.
my brain.
It doesn't. See, that's the issue. Y'all are always looking for what's different instead of what's the same. When I look at D, where am I going to start?
With the square root.
With the square root, okay? So I'm looking at 6 minus the square root of what? How am I going to rewrite that -8?
4.
4 times 2 is that -8?
I mean, -1.
Add the -1?
-1 times 2.
Alright? So I gotta make sure that I multiply to get what's underneath the radical. But I'm still dividing by 2, that's it. Okay?
Oh,
Still dividing by 2. So 6 minus 8.
I can't see.
6 minus,
The square root of all that is just -8.
yeah. Yeah, so -1 squared, and.
You need to be careful with your language.
You go ahead and write.
I'm not squaring -1.
Square root.
Square root of -1.
And square root of square root of regular 4.
You can just say 4. Positive 4.
Square root of 2.
Still all divided by 2. Okay? Then I'm going to simplify from there. Say again.
6 minus I do times 2 and square root 2.
What?
And then 2
Shannon,
divided by.
why are you shaking your head? Shannon, what's the square root of negative 1? I. So there's the I. What's the square root of 4?
2.
Okay. Can you take the square root of 2?
No.
So it's square root of 2. That's it. Don't make it more
Where does 6
complicated.
come from?
Shannon, it's been there the whole time.
The whole time.
It started with a 6.
Oh, okay.
Again, don't make it more complicated. I'm only dealing with the square roots right now, so I'm simplifying as I can. The division by 2 hasn't changed a single thing.
You don't divide nothing?
Well, at this point, now that I've simplified my radical, remember division has the same property as multiplication in that I can what?
Multiply? No, divide.
What major principle or property does multiplication have that you might use here? Distributive property. What can you do with division? Distributive property. So 6 divided by 2 minus, I would write as 2 root 2I divided by 2. What's 6 divided by 2? 3. What's 2 divided by 2? 1. So minus, that would just be a 1, so square root of 2I. The division didn't change a single thing. You had to simplify your radical. After simplifying your radical, right, you had to divide by 2. Make sense? That's it. That's all it is. So y'all ready to try C on your own? Yeah. Okay, so try C on your own within your small groups. Let me know if you have questions. At this point, LaShannon, go ahead and jump in. You need to jump in with group 4 or group 1 just so you have someone to talk to. Just grab your book and take it with you. Okay? If CD shows up, we'll let him jump into the other group. Don't forget, you got a small group. I'm looking for collaboration because you will help each other learn more. Try to turn the lights on, make it easier to see your book that you're writing in. And so be careful with the D, because here's 1, 2, 3, and then step 4. Had to get out of order. So ran out of room.
Is it different what group?
Either 1, 4, or 1. You might want your calculator with you.
I did 25. I did 25.
Yeah, for a while.
I'm so sorry.
I'm sorry for you.
I know, I have like new medicine and it's like supposed to help you sleep, but then when you wake up, it doesn't like turn off. You know, like it's supposed to like not make you sleep all day, but like,
You gotta, yeah, you don't have to wake up earlier with medicine like that.
that's the problem. I can't wake up in the first place. My parents literally came in and were like shaking me. My dad had to pick me up, put me on his shoulder and carry me to the bathroom. That man got a fake hip and like a messed up shoulder, like how he even do that?
You might need to go to bed sooner. What time did you go to bed last night?
9. What's up at 9?
Man, that thing knocked you out.
Early.
I might take half the prescribed dosage
Yeah.
in the future. Have you talked with, because I'll say this, it looks like you have a very, very, very similar answer
You're gonna be.
to Nathan. Just one small difference, talk with each other about it.
Okay, so negative 1 is
So
gonna be,
then,
so I put negative 1 first.
Yeah, that's what we, so basically, are
Can
we
you add them?
saying, of what are we trying to?
What's happening between the,
We're rewriting.
Those are being multiplied. Can you add before you multiply?
Factor out.
Yeah.
negative 1.
Right. That, it's like, that's, If y'all are both getting the same answer, you're probably doing great. You know what I mean?
We did square root of 25.
Sorry, I'm sorry, no,
The negative, or the square root of negative
Square root of
1
25.
times.
Be really careful right here. Is that I underneath the radical?
Equals square root of negative 1 times.
Yeah. That I right there, you magically put it underneath the square root.
Equals, I'm just literally copying what they did.
Don't forget you can divide by 2 here. Like 6 divided 2 is 3, 2 divided 2 is 1, so we simplified it.
Now you gotta factor it.
I would also suggest you look back at your last step or your second to last step. You're close.
Okay, into what, like 25 times
Okay,
2?
so one's gotta be a perfect square. So 25 is a perfect square, so you do 25 times 2.
Yeah, and then 25, or do we just pick two things that make 25?
I know you don't have to do after that. You just
5
do
and 5 or something?
Yeah.
What is that thing we used to do where we would like,
Factor tree.
yeah, and then we'd circle them and 5
The
times
prime
5
factors.
times 2 equals.
But you don't have to go to that point.
So we only go 1 now?
Does it matter? I don't think that matters. Give it 5.
Don't drop stuff off. You're gonna forget that 5 at the end.
I didn't know where to put it because I was kind of copying their thing and their thing didn't have a plus five, so I
It's just, it's still there. You
Yeah.
you just don't drop it off.
No,
Notice how I kept my 5 plus all that radical the whole way through. Did you find out where your mistake was, KJ?
Are you saying that? Put down.
Square root of negative 1 is fine. Look at your answer though versus what their answer is.
Oh,
Square
Negative one.
So like 5 plus.
Well, he had that earlier. Go ahead and fix, because the square root of negative 1 is I. Go ahead and write that down.
Right, plus
It is still I. Square root of negative 1 is I. Leave that there. I want y'all to look again.
Oh, yeah.
put 5.
Wait, who needs to be
this
in
needs
the
to
square
be,
root? We don't get the square root of 5.
Because square root of 25 is 5.
So
We
remember,
just keep this small root.
Oh, yeah, because
So
5
you can
is.
erase these.
Oh.
because remember, that's the whole thing. We can take the square root of 25. We cannot take the square root of 2. So it definitely matters. Or, yes. Remember, what all you're doing is you're taking the square root of what you can take the square root of. Can we all agree up to this point? We all get it through up to here? Yes? And so here's where we have to be careful, because I saw one student make this mistake, and this is a mistake that I have consistently seen throughout all the years that I've been teaching, where, alright, so the square root of negative 1 is I, square root of 25 is the square root of 5 times 2. What's wrong with that?
It's not square root.
It's not the square root of 5. Remember, I took the square root of 25 is what? 5. So that should be a 5, right? The square root of 25 is 5. Is it correct now?
No.
What's wrong? And that is the mistake that a lot of students make, is that they accidentally, or they flip or switch the one that they take outside of the radical. You're not taking anything out of the radical. All that you're doing is taking the square root. If you can take the square root, take the square root. Square root of 25 is 5. Square root of 2 I can't do anything with, so it's square root of 2. So 5 plus 5 square root of 2i. Is that less scary than it was?
Yeah.
Feeling better about that? And so just remember, we typically write the real component, or the real coefficient of the I first. That's why I did it that way, okay? I'm just gonna go ahead and let you know, I was planning on testing Wednesday. There's no way I can do the understanding check today, so we'll have to move the test to Thursday. Which really sucks, but we're gonna have to make it work. We still have at least 3 units that we have to do between now and Christmas.
We don't have.
Well, we have to. There is 1 unit on trigonometry that we will barely touch on, but if you take pre-cal, I know that Beasley does a very heavy unit on trig from the ground up.